Remember your Creator in the days of your youth. Greetings to you all in the name of the Lord Jesus Christ. Today we are going to learn about simple pendulum, and this is a very well known topic to you all because you have learned about this in 8th standard itself. So today under simple pendulum we are going to see time period, frequency, graph of length L versus T square, formula and simple numerical problem. Let us get into the class. Simple pendulum. A simple pendulum is a heavy point mass known as bob suspended from a rigid support by a massless and an inextensible string. An inextensible string means no matter how much you pull on it, it won't extend. When the bob is taken to one side and released, it starts moving to and fro. During motion, there are two positions where the bob stops and changes its direction. These positions are called extreme positions of the pendulum. Let's denote them by A and B. There is a moderate position between the two extreme positions. It is called the mean position of the pendulum. Let's denote it by O. When the bob is at rest, it is at its mean position, that is O. The motion of the bob, that is the motion of the simple pendulum, repeats itself after certain time. Such motion are said to be periodic or oscillatory motion. The bob completes one oscillation when it moves from mean position, goes to one of the extreme position and then to the other extreme position and return to its mean position again. The time taken by the bob to complete one oscillation is called the time period of the pendulum. We measure the time period by measuring the time required to complete an oscillation from the extreme position. It is difficult to measure the time period in one go. Here's a method to measure the time period of the pendulum. Mark the mean position of the bob on the floor. Take a clock to measure time, preferably a stopwatch. Keeping the string to the mean position and bring it to one side. Now release the bob and at the same time start the stopwatch. Go on counting the oscillations. Stop the stopwatch as soon as the pendulum completes 20th oscillation. Make a table and enter the time taken to complete 20 oscillation. Take few readings performing similar activities and note down all the readings. For each reading, calculate the time period of the pendulum by dividing time by number of oscillation, that is 20. Is the time period nearly same in all cases? Yes. You will find that the time period is same in all cases. Next, amplitude. The maximum displacement from the mean position is called amplitude. And it is represented by the letter A and it is measured by the unit meter. Oscillation. The motion of the mass from its extreme position A to C and back to A is called an oscillation. Otherwise, the bob completes one oscillation when it swings from O to B, then to A and returns to O. So this is called oscillation. Next we are going to learn about frequency. Frequency is the number of oscillation per second. That is F is equal to N by T. Now let us learn the laws governing the time period of a simple pendulum. The first law states that the time period of oscillation of a simple pendulum of constant length is independent of its amplitude. Let us conduct an activity to verify the first law of a simple pendulum. To verify the first law, the apparatus required is a metallic bob, a thin and strong string of length 120 cm, an iron stand with a clamp, a cork, a meter scale, and a stopwatch. Place the iron stand over a table. Tie the metallic bob and suspend it from a stand with the help of a cork and a clamp. The simple pendulum is set up. Fix the length for the pendulum, say 50 cm. Pull the bob to a side such that the amplitude is about 10 cm and allow the pendulum to oscillate. With the bob at its one of the extreme position, stop the stopwatch, count 20 oscillation and stop the stopwatch. Note the time taken for 20 oscillation. Calculate the time taken for one oscillation, which is the time period of an oscillation. Tabulate the readings. Now repeat the procedure with the amplitude of 15 cm and 25 cm. Don't change the length of the pendulum. Calculate the readings. You will observe that the time period of the oscillation remains the same for different amplitudes. Thus, the period of oscillation is independent of the amplitude, provided the amplitude is small. Just verifies the first law. From the first law, it is clearly understood that the time period does not depend upon the amplitude. The second law of the simple pendulum states that the period of oscillation of a simple pendulum of constant length is independent of the size, shape, mass, and material of the bob. Second law of simple pendulum states that the period of oscillation of a simple pendulum of constant length is independent of its size, shape, mass, and materials of the bob, provided it is not very light, such as cork. Let us verify the second law of the simple pendulum. Take 3 bobs of different masses and different materials. Set up a simple pendulum with the first bob of fixed length, say 50 cm. Choose any amplitude, say 5 cm, and pull the bob to 5 cm. Now release the bob and make it to oscillate. Start the stopwatch when the bob is at one of the extreme position. Count 20 oscillation and stop the stopwatch. Note the time taken for 20 oscillations. Calculate the time taken for one oscillation, which gives a time period of the simple pendulum. Tabulate the readings. Now, repeat the procedure with the second ball and the third ball by keeping the length of the pendulum and the amplitude the same. Then tabulate the readings. You will observe that the period of the oscillation does not change with the mass and the material of the bob, provided the length of the pendulum and the amplitude are constant. Just verifies the second law. From this activity, it is clearly understood that the time period does not depend upon the size, mass, or shape of the bob. The second law of the simple pendulum states that the period of oscillation of a simple pendulum of constant length is independent of the size, shape, mass, and material of the bob. From this activity, it is clearly understood that the time period does not depend upon the size, mass, or shape of the bob. The third law of the simple pendulum states that the time period of the oscillation of a simple pendulum is directly proportional to the square root of its length for a given place. That is, T directly proportional to the square root of L. Let just equation be 1. Equation 1 can be written as square root of L by T is equal to constant. On squaring the equation, we get L by T square is equal to constant. That is, now verify the third law of simple pendulum. Set up the pendulum with a metallic bob as we did in the first law. Select the length, say 50 centimeter. Pull the bob to the side such that the amplitude of the pendulum is not greater than 5 centimeter and then release it. The pendulum starts oscillating. Stop the stopwatch when the bob is at one of the extreme position. Count 20 oscillation and stop the stopwatch. Note the time taken for 20 oscillation and tabulate the readings under the head trial 1. Repeat the procedure with the same length and amplitude. Note the time taken for 20 oscillation and tabulate the readings under the head trial 2, trial 3 and so on. Calculate the average time taken for 20 oscillation and then write the average for 1 oscillation. Tabulate the readings. Now find the value of L by T square for the given length of the pendulum. Now increase the length of the pendulum by about 10 centimeter and repeat the procedure to find the value of L by T square. Repeat the procedure 3 all by increasing the length of the pendulum by 10 centimeter every time. Tabulate the readings. You will observe that the time period of the pendulum increases with its length and the value of L by T square is the same in all the cases. Just verifies the third law. Thus, based on the laws of the simple pendulum and its experimental result, the time period of the simple pendulum is given as T is equal to 2 pi root of L by G. Seconds pendulum. If the time period of a simple pendulum is 2, then we say it as a seconds pendulum. We know that T is equal to 2 pi root of L by G, where L is the length of the pendulum, T is the time period and G is the acceleration due to gravity. Now, we have to square the formula T is equal to 2 pi root of L by G. Thus, if you square T, it becomes T square, and if you square 2, it becomes 4 pi square, and if you square the square root of L by G, the square root will go off and you'll get L by G. Now, from this formula, you're going to write the formula for length. That is, L is equal to T square into G divided by 4 into pi square is equal to the value for T. That is, the time period for a second pendulum is 2. So, you have to substitute 2 square into the gravity. The value for acceleration due to gravity is 10. So, you have to write 10 divided by 4 into, you know the value for pi, that is 3.14. So, 4 into 3.14. It becomes 40 divided by 39.43. So, if you divide these two, you will get 1.01 meter. That is 1 meter. Okay, we can round it to 1 meter. So, the length of the second pendulum is 1 meter. Now, once again, I am going to explain how to find the slope from this graph. Slope formula, that is S is equal to vertical change divided by the horizontal change. Now we are substituting slope S is equal to y2 minus y1 divided by x2 minus x1. Now tell me what is y1 and y2. Here if you see the coordinates of P and Q, the y1 is 1.61 and y2 is 2.82. So now we are substituting the value 2.82 minus 1.61. And just like that, x2 value and x1 value, see the graph and tell to me. And here the x1 value is 0.4 and x2 value is 0.7. So 0.7 minus 0.6. By substituting the value, you will get 1.21 divided by 0.3. By dividing these two numbers, you get the slope S is equal to 4.03. This is the way you have to find the slope from the graph. Now let us see how to calculate the acceleration due to gravity G once again. We know the formula for G. G is equal to 4 pi square divided by S is equal to 4 into, you know the value for pi, that is 3.14. You have to square that one, divided by S value just now we found in the last clipping, that is 4.03. Now if you divide these two numbers, you will get 39.4 divided by 4.03. If you divide these two numbers, then you get G is equal to 9.78 meter per second square. So using this graph and using the simple pendulum, we can calculate the acceleration due to gravity. That is G is equal to 9.78 meter per second square. Now let us discuss simple numerical problems in simple pendulum. The first question, a simple pendulum completes 40 oscillations in a minute. Find its frequency and time period. The formula for frequency, we know that frequency is a number of oscillation in 1 second. So frequency is equal to n by t, that is n is number of oscillation and divided by t, t is the time taken. Here the number of oscillation given is 40 and divided by time, here they given as a minute. In a minute, you have to convert this minute into second. We know that 1 minute is equal to 60 seconds. So you have to substitute 40 by 60, you will get 0.67 second per second. Next you have to find the time period. The formula for time period is equal to T is equal to 1 by F. Here 1 divided by F, just now we found, that is 0.67. So 1 divided by 0.67, you will get 1.5 second. So this is the first formula, this is the first numerical problem. Now the second numerical problem is the time period of a simple pendulum is 2 seconds. What is its frequency and what name is given to such pendulum? And time period given here is 2 seconds, and we know the formula for frequency. Frequency is equal to 1 by t, that is 1 by time period, and the time period is 2, so you are substituting 1 by 2. You know 1 by 2 value is equal to 0.5 per second. And here we know that if the time period of a simple pendulum is 2 seconds, then we call that type of pendulum as seconds pendulum. So since here the time period is 2 seconds, such a pendulum is called the seconds pendulum.